Hi. Okay, so last time we discussed few concepts related to E by M ratio, that is J.J. Thomson experiment. I hope you people remember because we did solve a question in previous class that was actually making reference to E by M ratio, but we have not discussed E by M ratio. There was another question that we were supposed to solve in the previous class, and I forgot to share the notes with you people as well. So, question is in front of you. Try to solve this one. Once you are done with solving it, let me know. I will scroll down so that you can solve the remaining part. Or what else you can do? Just take the screenshot of this first page. Okay, take a screenshot of the first page so that you can continuously keep on looking on the page number 2. Solve the question. Once you are done, let me know. We will discuss the answers. And it will be great if any one of you remind me to share the notes somewhere around, you may say 10 p.m. onwards, because that is the time at which I'm free and I can share the notes actually. Because most of the time, what happens, I have back-to-back classes and I don't share notes during that time. Okay, now solve this question. Once you are done with it, let me know. We will discuss the answers. Okay, I think almost all of you are done solving the question. Let's quickly discuss the answers. So what question says, a charged particle of mass m and charge minus q is traveling through a vacuum at constant speed v. It enters a uniform magnetic field of flux density b. The initial angle between the direction of motion of particle and the direction of magnetic field is 90. This 90 is actually very important because I hope you remember when a charged particle enters the field perpendicularly at an angle of 90 degree, then force actually behaves like centripetal force. Particle will keep on moving in a circular path. If charge enters at angle, then particle will never move in a circular path. It will form a helical path. I hope you have that point in mind because we have discussed in one of the classes. Explain why the path of the particle in a magnetic field is the arc of a circle. Why? You will say force is given by QVB. This force is perpendicular to both V and B. What is important for us is this force is perpendicular to velocity. And whenever force is perpendicular to velocity, the force will never increase or decrease the speed. It just changes the direction. It means that it will behave like centripetal force. I guess in previous few questions, we did mention this thing. So whenever they say why it is following a circular path, you need to mention force is perpendicular to velocity. Since force is perpendicular to velocity, it will behave like a centripetal force. So how many of you actually mentioned these points? Okay, all of you. The radius of the arc in A is R. Show that the ratio Q by M for the particle is given by the expression. So we know that F is equal to QVB. This F will behave like centripetal force. So MV square over R, V and square will get cancelled. So if we need the value of Q by M, it will actually become V over B R. So it was pretty simple. How many of you actually did the same working? Okay, next. The initial speed of the particle, V of the particle is 2 exponent 7 meter per second. The magnetic flux density B is 2.5 extra minus 3 Tesla. The radius of the arc in the magnetic field is 4.5. Use these data to calculate the Q by M. So if you need the value of Q by M, you just substituted the values. So V is 2 exponent 7 divided by B is 2.5 exponent minus 3 and R is 4.5 exponent minus 2 because we need SI unit. If I simplify this whole thing, what are we getting as the answer? Anything around 1.8 exponent minus 11? Because this is the standard value of E by M ratio quite possible, you people remember. The path of the negatively charged particle before it enters the magnetic field is shown in figure 6.1. Magnetic field into plane of the paper. So this is the direction of magnetic field into the plane of paper. If I apply right hand rule, so I will be putting right hand like this. I mean, I'm just imagining surface is in front of me. So I will put right hand like this. Fingers are in the direction of field into the surface. Velocity is right. Push of the palm is up. Right hand rule always gives you the direction of positive charge. Since in the question they specifically mention in the first line charge is negative. So this particle should be deflecting in downward direction. So what you need to do, you need to draw an arc. And once you have drawn an arc, when it comes out, it will keep on traveling in a straight line. So you have to draw some path like this. While drawing this arc, take care of one thing, that this arc should be of constant radius. What does constant radius mean? If I try to complete a circle, so this arc should appear as a part of that circle, right? But I generally think whenever you draw this arc, that will be correct. But The curved path will remain inside the field. The moment it comes out of the field, it will start moving in a straight line. And how will you determine the direction of a straight line? Tangent to that point. What does tangent to that point means? If you look at this point, the straight line which I have drawn is actually the tangent to the circular path. How many of you actually drawn the similar path?
Sir, can you explain the tangent part again?
Okay, see, if you want to draw this thing, number one, you must have drawn a curve. So it will remain curved inside it only. Now, when it comes out of the field, it should keep on traveling in a straight line. So just imagine it was a circle like this. So this is the last point. Just draw tangent here, so it will go like this. Now I'm getting it.
Yes, I got it. Thank you.
Sir, for the previous question, could you please show me your answer? Sir, I got 1.3 exponent 11. Is it minus 11 or 11?
No, it is plus 11 actually. It is actually plus 11 because if you remember A by M, so in the denominator we have minus 31, so in numerator we will be getting surely positive value. Plus power 11 is correct answer. Okay, so we are done solving it. Today we will be discussing Hall effect, Hall probe. I guess we have one question related to it. Then we will be discussing something related to moment on a current carrying coil. Okay, just look at it. What I'm going to explain is something we have already discussed in bits and pieces. Today we will be combining it. Let's say we have a piece of conductor. That piece of conductor could be a metal plate, something like this. Let me draw it first. Let's say we have a piece of metal plate, something like this. Since it is metal, so it must be a conductor. If it is a conductor, it must be having free electrons. What I did, I connected this piece of metal to certain battery or cell. That battery or cell will provide electricity to it. So what I'm doing, I'm not drawing the complete circuit. This is one wire. This is other wire. And the current will be flowing in this direction. The current will be flowing in this direction. For the sake of simplicity, I'm considering this current as electronic current. It will make things easier for us. This is actually electronic current. So what I have done, I have taken a piece of metal. I connected that piece of metal to a battery or to a cell that will be providing current. The direction of current that I have shown is actually of electronic current because I will be doing all the working in context of electron. But it is not necessary. You can apply the same working on conventional current as well. Your result will stay the same. What will be the difference that we will be discussing in the end? But if I consider electron only, things will be a bit easier for you. So what I'm doing, I'm considering electronic current. That electronic current will move from top to bottom to top. Let's apply a magnetic field. That magnetic field is actually into the board. So how to draw into the board? For into the board, I'm drawing this sign, this cross. I hope you remember the cross means magnetic field is into the board. I mean, if this is the surface, this is the piece of metal which I'm talking about. So magnetic field will be like this, just like this pencil into the surface. Now, what will actually happen? The current will start to flow. The moment current enters that metallic block, what will happen? There is a magnetic field which is into the board. What will happen? Electron will not keep on traveling in a straight line. For example, ideally, if there wasn't any magnetic field, electron will keep on traveling in this along this line. If there wasn't any magnetic field, electron would keep on traveling in this straight line. But in the presence of magnetic field, what will happen? The electron will take a curved path. And when I say electron will take a curved path, so just tell me one thing. Electron will be shifted towards right side of the metal or towards left side of the metal. Just answer this question. Rest working I will be doing.
Towards the left side.
Think again. I mean, we have electronic current. Electrons are traveling. Magnetic field is bound to that metal plate only. The moment electron enters the metallic piece, towards which side it should be deflected. By the way, let me write. This is my left and this is my right. Yes. Where should electron deflect? Towards left or towards right? I don't think so. It's a very
Towards
good
right.
question. Towards right. Electron will deflect towards right. Just apply the right hand rule. How to apply right hand rule? Surface is exactly in front of me. I will put fingers like this into the board. Velocity is upward. So push of the palm is towards left, but right hand rule is for a positive charge. So electrons should deflect towards right. So ideally speaking, electron will follow a path like this. Are you people getting it? That electron will follow a path like this, a curved path. Okay, let me make a little neat. The electron will follow some path like this. Electron will follow a curved path. Why it is following a curved path? Because electrons are moving in a magnetic field, and magnetic field will force them to follow a curved path. How many of you are actually getting this idea? What I'm trying to explain? Okay, if you people are getting it, the moment electron shift towards right, so can I say the right hand side of this block starts to behave like negative because their electrons are actually accumulating. If this side is becoming negative, then can I say this side will start to behave like positive? Because when we talk about potential, so if one side is getting negative, it means that in relation, we can say relatively other side is getting positive. So it means that when current is passing through that piece of metal, some potential difference is created across the edges. For example, just imagine it is the piece of metal. When electrons are traveling, they are curving this side. So this side become negative. This side will become positive. So I can say some potential difference is created across the two sides of the metal plate. One will become positive, one end is negative. So if I connect a piece of wire here, if I connect a piece of wire here, this end is positive, this end is negative. Some potential difference is created across the metal plate. This potential difference is denoted by VH, and it is known as Hall voltage. This VH is known as Hall voltage. Now, before we start driving certain relationship for this thing, we should be very clear about what we are actually going to do. Electrons are traveling. The moment they enter the metal plate, because of magnetic force, they will start moving towards right. So right becomes negative, so left will become positive. Some potential difference is created. This potential difference is known as Hall voltage. This distance is D. The thickness of the metal plate is T. T is this thickness. T is the thickness of the metal plate because we will be using it in upcoming part. By the way, how many of you are actually clear till here? Okay, if all of you are clear till this part, now what will happen? Remember, if I'm not wrong, in last class we did solve a question. Quite possibly we answered this thing. Previously we had magnetic field only. As the current keeps on passing through it, the potential difference, the whole voltage will keep on increasing. And in the presence of potential difference, I can say an electric field is generated. I must say an electric field is generated. Why? Because if you remember this equation, potential difference is given by E times delta R. Here, potential difference is denoted by VH, Hall voltage, and delta R is denoted by D. So VH is given by E times D. So there is some electric field which is given by VH over D. Once we have electric field, I can say there must be some electrostatic force which is given by Q times E. Remember this because we did use this equation previous class as well. It is nothing but just a modified form of E equal F over Q. So F is equals to Q times E. Since I'm talking about electrons, so Q can be replaced by E and E is replaced by VH over D. This is the electric force. Initially, electron was under the influence of magnetic force only. And that magnetic force F is given by EVB. I'm calling it equation number 1. Why EVB? Because it should be QVB sine theta. Theta is 90 degrees, sine 90 is 1. And Q is represented by electron because I'm specifically talking about electron. So we know the value of magnetic force. We know the value of electrostatic force. I can equate them. So if I say equate 1 and 2. So what was equation 1? EVB. What is equation number 2? EVH over D. E and E will get cancelled. So if we talk about VH, it will become DVB. Are we getting it till here? Okay, if we are getting it till here, so one thing we would be knowing, and that one thing is D is the width of the plane. We would be knowing if I show you on the diagram. D is the width of the plane. We know already. B is the strength of the magnetic field. That is something because we have applied the magnetic field. We would be knowing what is the value of magnetic field. The only parameter that we are unaware of is actually V, and V is the velocity of electron, right? Remember, in AS level physics, we used to use an equation I is equals to NAEV. Electronic current is given by NAE times V. How many of you remember this equation? Okay, almost all of you. So if I calculate V, it will be I over NAE. Put this in above equation. Hall voltage will be D I over NAE, and then we will be having B. Now, if I say, what is this N? N was number of electrons per unit volume. Remember this thing, this N was electronic density.
Sir, we can't hear you. Sir? Sir, we can't hear you. Sir, I think you're talking, but then I can't hear you.
Okay, so actually I got disconnected, but now all of you can hear me. So let me share my screen first. Meanwhile, if any one of you heard my question, you can answer the question. How to calculate cross-sectional area of the metal plate?
D into the thickness.
D into the thickness. Okay, do you people agree? If we need to calculate area, cross-sectional area of this piece of metal, what we will be doing, we will be multiplying D by T. So in this equation, what we can do, okay, I hope actually you were able to hear everything, even you heard the question previously as well, right? Okay, now put the values. So VH equal DIB divided by N. Instead of area, I can write D into thickness time E. This D and D will actually get cancelled. When D and T actually get cancelled, so we will end up with Hall voltage is equal to I times B divided by NTE. This specific equation is for electrons only. But remember one thing, it is not necessary that electron is traveling. In different materials, different ions can behave like a charged carrier. So if you want to make it generalized, what we can say Hall voltage is I times B divided by NTQ, where Q is the charge which is actually traveling. Are you people getting this working? I mean, if you have any confusion in this working, feel free to ask. Then we will talk one or two more things related to Hall probe, and then we will move forward. Okay, if everything is clear, just tell me one thing. No doubt, Hall voltage will be a very small value. Hall voltage will be a very small value. If you look at this equation, I is the current, B is the strength of the field, T is thickness, Q is charge. N is actually the electronic density or charge density. What do you think? If we have more value of N, then Hall voltage will be more or Hall voltage will be less?
It will be less.
Less, because they are actually inversely proportional to each other. To keep this value of N low, because in every conductor, electron density is actually very high. So what we do, we prefer semiconductors. We haven't discussed semiconductors yet, but you must be having some understanding from IGCSE level. In semiconductors, we will be having less density of the carrier. So to make Hall probe, to make the chip which can serve as Hall probe, we prefer semiconductor, because sometimes in exam they can ask this thing. Why semiconductors are preferred to design Hall probe? Just because of the inverse relationship between Hall voltage and electron or charge density. Since in a conductor charge density is very large, so Hall voltage, which is actually very low, will decrease further. So instead of conductor, we use semiconductor. So the preferred material is actually semiconductor. And why? To keep N low. Now, where do we use Hall probe? Any example? In devices, nowadays, all of you must be using some smartphone or some tablet or iPad. All these devices have a sensor which is known as proximity sensor. Ever heard about it? By the way, how many of you are actually familiar with this thing? Proximity. Okay, when I just scroll the screen up and down, I just do it to make sure that everything is fine and you people can hear me. By the way, how many of you have ever heard about this proximity sensor in a device? Okay, so if you have heard about it, does anyone of you know what does it do?
Sir, I don't know the exact definition, but when you attend a call or like when you move your phone close to your ear, it automatically switches off the screen so you don't touch it accidentally.
Exactly. This is the meaning of proximity. Proximity means in the nearby. Proximity means in the nearby. For example, what actually happens when you make a phone call? Phone is in front of you. You're using some Bluetooth device or something like it. Screen will remain on. The moment you bring your phone close to your ear, uh, before even touching the ear, the screen will go off. Why? Because it sense that's something. And how does it do it? Using the proximity sensor, and all these proximity sensor actually make use of Hall Pro. So there are number of devices which works by detecting the objects. For example, proximity sensors in these smart devices keep the screen off or on. If any one of you is using any Samsung device, you can even check it. If I'm not wrong, if on, I don't even remember whether it is right or wrong, but I have used this thing. If you are using a Samsung device and you dial this code, it will open up a menu. And in that menu, there must be one button of proximity sensor. And what you can do, if you put your device like this and bring hand close to it, you can see the values actually changing. Because those proximity sensors actually sense the presence of field. Because magnetic field is all around, current is all around. So those proximity sensors working on it. Similarly, quite possible in many automatic doors, when you go to mall, you stand in front of a door, the door actually get open. They make use of proximity sensor as well. So most of the time they are using photoelectric effect as well. But Hall Pro can be used even there as well. Right, so we should be knowing what is Hall Probe, what is the purpose of Hall Probe, where we can use it. The major use of Hall Probe is the proximity sensor. And proximity sensors are the devices which can detect object even without touching them. Even without touching them. Okay, so I guess in the past paper booklet, we must be having a question in which they just use Hall Probe, I guess. Okay, there's a question, but the problem is in this question, they, if you can see something which I have actually highlighted, we are due to study a topic that is alternating current. So quite possible, I will teach you that topic first because in two questions we didn't attempt 1 mark part because of this thing, and in this question we will be needing that concept as well. So we will be solving this question because this is the only question related to Hall Probe in past, you can say 8 or 9 years of paper 4-2. So we will be attempting this question after discussing that topic. So currently we are not solving any question. Okay, before I start teaching you alternating current, and then we will move on to electromagnetic induction. One thing that we should also be knowing, remember this equation? F is equal to ILB sin theta. Magnetic force on a current carrying conductor, we have already discussed this equation. Whenever a current carrying conductor is placed in a magnetic field, the magnetic field will exert a force, and that force is given by ILB sin theta. Now, what if that conductor is actually in the form of a coil? What does it mean? Let's say we have a north pole here. This is north. We have a south pole here. And we have a conductor. That conductor is in the form of a rectangular loop, something like this. Let me make it a little better first. Okay, the conductor is in the form of a rectangular loop, and the name of this loop is A, B, C, and D. So magnetic field is from north pole to south pole. It will be towards right. This rectangular loop is actually fixed on an axle. Let me draw it first, then I will explain what is the purpose of it. This is known as X axis. This is the axle across which something can rotate. I hope you understand what is the purpose of axle in cars. For example, if this is the object and you fix it like this and you start rotating it, so the line across which it will be rotating, let's say this line will be known as axis of rotation, which is also known as axle. So what we have done, we have fixed this coil ABCD, rectangular coil on an axle, which is XX dash. And then we connected this to a battery. And battery is connected in a manner that current is going like this, from A to B, and then from C to D. Because this end is connected to positive terminal of the battery, and this end is connected to negative terminal of the battery. Now you have to decide just one thing. There are total 4 conductors in this rectangular loop. A to B is 1, B to C is 2, C to D is 3rd, and D to A is 4th. A rectangular loop is made up of 4 conductors. Let me draw here so that you can relate. Those 4 conductors are like this: L1, L2, L3, L4. There are total 4 conductors in this magnetic field. If I ask you, these 4 conductors are placed in a magnetic field, you have to decide just 2 things. Which conductor will experience the force and which conductor will not experience the force? Are you getting my question?
Yes,
We
sir.
have 4 conductors. We have 4 conductors in this magnetic field, and we have to decide just 2 things. Which conductor will be experiencing a magnetic force, which is given by ILB sin theta, and which conductor won't be experiencing the force? This is first thing. And second is, on what basis you can say some conductors are not experiencing the force? So if any one of you want to answer this, you can.
Sir, only L1 and L3 will experience force, L2 and L4 won't, because L2 and L4
Why?
are parallel to the field, which makes the angle between them and the field 0, and sine 0 is 0.
So how many of you agree that only side AB and CD will experience the force? Why? Because they are perpendicular to the field and force will become maximum. But if we look at BC and AD, they are actually parallel to the field. And whenever conductor is parallel to the field, there won't be any force. So we can say there will be force on side AB, this one, and side CD, this one. Are all of you getting it? That we will be having force only on side AB and side CD. If any one of you is confused or have confusion, you may ask. Okay, so one thing we have decided. We have discussed the reason, the theta. When theta is 0, force is 0, theta is 90, force is maximum. What should be the direction of force? I mean, if I say identify the direction of force on side AB, so what should be that direction?
Into the board.
Into the board. Why into the board? Because field is from north to south. Current in AB is upward. So technically speaking, I need to put my right hand like this. Field is left to right, current is upward. So push of the palm is into the board. If force on side AB is into the board, then what about force on side CD?
Out of the board.
By the way, I hope all of you are getting it. The force here will be actually out of the board. How many of you are getting it? That force on side AB is into the board and force on side CD is out of the board.
Sir, could you repeat that because I did not get that point? About into and out.
Okay. Okay, see, if you apply, Ma'am, if you apply right hand rule, so field is north to south, I should put right hand like this. Current is upward, so push of the palm is into the board. But if you look at C to D, field is like this, but current is downward, so I need to put my right hand like this. So push of the palm is out of the board. Are you able to visualize?
Yes, yes, sir.
So force on side AB is into the board, force on side CD is out of the board. Now just imagine, this is the coil, one force is in, other force is out, it is fixed from the two edges. What will happen? It will start to rotate. Do you agree? How many of you agree that it will start to rotate? And I hope you remember, turning effect of force is actually known as moments. Turning effect of force is known as moment. So the topic that we actually want to discuss is basically moment of magnetic force on a current carrying coil. So the topic that we are going to discuss is moment of magnetic force on a current carrying coil. Now, if I'm looking at this setup from the front, what does from the front mean? Because my assumption is that coil is placed like this. Here we have north, here we have south. So when I'm looking at this coil from the front, the way you can see, you will be able to see only one side, this one. So if you look at the labeling on this diagram, if I'm looking at the coil from the front, can I say I will be able to see side A to D only? Do you agree? I mean, what I'm trying to say, just look here. I will be able to see this thing. I can see north. I can see south. South. And there will be a coil for which I can just say A and B, and this is the point which is actually the axis across which the body will be rotating. Do you agree that I will be able to see this thing if I'm looking everything from the front? Is it clear? Are you able to visualize? Because my entire working is based on this diagram actually. So all of you should be very clear about this thing. Okay. If I say length of the coil is L, so this side is actually L, and width of the coil is B. So A to B is L, C to D is L, B to C is small b, A to D is small b. Length into breadth, simple symbols I'm using. So may I know what is A to D, L or B?
It's B.
It's a small b. So I'm writing a small b here. The force on side AD is actually into the board, but the way I am drawing it, I'm calling it downward just to make it easy for you to understand. If this force is downward, then this force should be upward because these forces are acting in opposite direction. Remember, two forces which are equal in magnitude, opposite in direction, acting parallel to each other are known as
Couple.
couple. In moments in AS physics, we did discuss this thing. When we talk about couple, what does it mean? Two forces which are equal in magnitude, opposite in direction, and acting parallel to each other. And it should happen. Why? If I talk about force on side AB, it should be ILB. So force on side CD should also be ILB because we have same current, same length, and same field of induction. So both the forces are equal in magnitude. The only difference is if one is into the board, other is out of the board. If one is upward, other is downward. So it means that they are equal in magnitude, opposite in direction. So they will form a couple. And remember how to calculate moment of a couple. Moment of a couple is given by force into distance between the two forces. Can I say that distance is actually B? Is it clear? That moment of couple is actually given by magnitude of one of the forces and the distance between the two forces. Now this force is actually ILB into B. If you look at this, it will become L into B. And I hope many of you can recognize this length into breadth is actually area. So this equation will become torque is equal to or moment is equal to IBA. This is a coil of single turn. Single turn coil mean we have just one turn in the coil. But what does it mean? Let's say I have a long piece of wire. I start bending it. So I start from this point. This is one loop. I twist it again, two loops. I twist it again, 3, 4, 5. The way if you look at helical spring, it has large number of turns. So rectangular coin can have many turns. So this working is valid for one turn. If we have two turns, moment will become 2 IBA. If we have 3 turns, it will become 3 IBA. If we have n turns, the formula will become NIBA. So we can say for n turns, formula will become NIBA. Usually in books, it is arranged like this. I don't know about other countries, but in Pakistan, we usually have this name. So quite possible, the author is Pakistani and he arranged symbol in this form so that the student can remember this equation is that this is actually Bina. So torque is given by BINA. But this formula is valid only when plane of the coil is parallel to the field. The other derivation is not part of this syllabus. I will be concluding it directly, but listen very carefully. If this is the coil and this is the field, my entire working is on this assumption that side AD is parallel to the field. But it won't remain like this because the coil have to rotate actually. So generally, if you want to calculate this moment is given by Bina cos alpha. What is this alpha? This alpha is angle between plane of coil and field. What does it mean? Just imagine this is the field and this is the coil. May I know what is the angle between them? Can I say
0
this
degree.
angle is actually 0? This angle is 0, right? But when coil is rotating like this, it must be having some angle with it. When coil is like this, what will be the angle between them? 90 degree. And when angle is 90 degree, cos 90 is 0, torque will become 0. So remember this thing. Magnetic moment on a current carrying coil is maximum when coil is placed parallel to the field. The moment coil rotate and become perpendicular, the moment actually becomes 0. The moment actually becomes 0. So this small topic actually was left from the portion of magnetism where we actually discussed I and B sin theta. I didn't discuss this thing, so I thought to explain. I'm just giving you 2-3 minutes. If you have any doubt, any confusion related to this thing, you may ask. Otherwise, I was thinking to start electromagnetic induction, but I think we should discuss that alternating current portion first so that we can solve the part we have actually didn't attempt yet. So I will join you back in 2 minutes. Meanwhile, if you will be having any question, you may ask.
Sir?
Yes, ma'am. And yes, ma'am.
Sir, could you repeat the last part? The part about the angle? Yes.
Okay. See, what I was saying, this torque is maximum when plane of the coil is parallel to the field. I mean, if you look at this diagram, what I have assumed here, the magnetic field is from left to right like this. Do you agree? I just draw a blue line
Yes.
towards right.
Yeah.
So what is the angle between coil and the field? Can I say angle is 0 degree?
Yes.
So I will say alpha is 0 degree case. But the coil will rotate. And when the coil rotates, it will be according different positions. For example, let me explain it further. This is the initial position. this coil will actually rotate in anti-clockwise direction. So after some time, it will be like this. Then after some time, it will be like this. Yeah, I'm getting it? Because the coil will keep on rotating in anti-clockwise direction, right? So in this position, which I just highlighted, if I draw a magnetic field, it will be like this. Can I say angle is 90 degrees?
Yes.
This is the point where torque is actually zero. This is the point where actually moment is zero, because whenever angle is 90, moment will become zero. And this is the point where moment will be maximum. So in last part, I was trying to explain this thing, that actually the equation BINA is a specific case when coil is actually parallel to the field. But coil won't remain parallel to the field all the time. During the rotation, it must be perpendicular to the field. And at that point, moment will become zero. You know, I'm getting it?
Yes, sir. Yes. Understood.
Okay. Yes, ma'am, your hand is raised. You want to ask something?
Sir, I wanted to ask, like, why is it cos theta? Why not sine?
Okay.
Like,
The thing is, if we have given this equation, let me try explaining. Quite possible you get it. See, the original position of coil is like this. So this is the axis across which we are doing the working. So we can say this distance is actually B. Now what will happen? The coil will rotate. When the coil rotates, let's say it acquires some position like this. Okay. The force will be like this. Here it is in downward direction, here it is in upward direction. To calculate the moment, actually we need the perpendicular distance between the two forces which are forming couple. So that distance will be this distance actually. That distance will be this distance. Now, if you have understanding of vector, you will surely agree. So this side is actually B. This angle is alpha. So if I need this distance, it should be B cos alpha. I'm getting it.
yes, sir. Now, yeah, okay.
So it will become B cos alpha. Now, if it becomes B cos alpha, if I say calculate moment now, you will say moments is equal to force into moment arm. Now, this time moment arm wouldn't be B. Moment arm will be B cos alpha. Force will remain IBA. So if you combine this B and, in fact, force will be ILB actually. Force will be ILB. If you combine L and B, it will become area. So you will ended up with this thing, IBA cos alpha for one coil. And for n turns, this formula will simply becomes NIBA cos alpha, which I write like this, Bina cos alpha. I'm getting it.
Yes, sir.
Now I have actually explained everything. So if any one of you is wondering now, so coil is moving, you change the angle, you change the momentum, but you are not changing the value of force. By the way, did any one of you think of it? I mean, how many of you actually thinking that why I'm not changing the value of force? Because I changed everything, I didn't change the value of force. Why I'm not changing? Just try to visualize. If you put a rectangular coil in the field like this, and just keep on rotating the coil, this L will always remain perpendicular to the field, no matter what. this L will remain perpendicular to the field. So the force ILB sine theta will always remain ILB. Anyways, uh, if you are getting it, it's fine. Otherwise, what we should be knowing is how to calculate moment on a current carrying coil. Okay, let me do one thing. I am just uploading a question related to moments so that you can solve, have little practice, then we will proceed from here. So just give me a minute. Okay, I just uploaded a question on Google Classroom. So try to solve that question. Once you are done, raise your hand. We will discuss the answers. Okay, how many of you are done solving this question? So let's quickly discuss the answers. A small rectangular coil ABCD contains 140 tons of wire. The side AB and BC of the coil are of length 4.5 and 2.8 respectively, as shown in figure 6.1. The coil is held between the poles of a large magnet so that the coil can rotate about and access to its center. The magnet produces a uniform magnetic field of flux density B between its pole. When the current of coil is 170, they have given you the maximum torque. Now, this is important. The torque is maximum. For the coil in the position of maximum torque, state whether the plane of the coil is parallel, normal, or in the direction of magnetic field. So I hope all of you must have mentioned parallel, right? Okay, coil should be parallel. Now next. For the coil in position shown in figure 6.1, calculate the magnitude of force on side AB of the coil. So if you need the force on side AB, you must be using F is equal to ILB. And if you want to use sine theta, it is something else. But what is tricky here actually? How many turns we have in the coil? 140. So whatever answer you will get using ILB, it is for one turn only. So to get the total force, we need to multiply this value by N actually. So the value of current is 170 milliampere, means 170 exponent minus 3. Can we use this equation? I guess we can solve it directly as well. Torque is given by force into moment arm, because torque is also given, which is 2.1 exponent minus 3. Force is unknown, and the value of moment arm should be B, which is 2.8 centimeter. Since we use SI unit, so it will be 2.8 exponent minus 2. So if I simplify this thing, what I will be getting?
0.075.
0.075. Okay, how many of you are actually getting this answer? Okay, next part. Side BC of the coil. Now, if you look at side BC, we have already decided this thing, that force on side BC will be 0 because it is actually placed parallel to the field. Use your answer in B1 to show that magnetic flux density B between the poles of the magnet is 70 millitesla. Now, this is why I couldn't use the formula I was trying to use for side AB, because we didn't have the value of B actually. So what we can do for B, we can say F is given by ILB sine theta, right? Since we have n number of turns, so I think we know all the values. In this equation, only B is actually unknown. So put all the values in this equation. Were we able to verify this thing? Is B coming close to 70 millitesla?
Yes, sir.
Okay, so we will resume from here in next class. So in next class, we will be starting topic of AC current, alternating current, because so we won't be able to complete that topic before discussing mutual induction, because there's a topic of transformer as well. But it's better to cover that AC thing before anything, because in many questions, a part is attached which is actually related to that. So we will resume from here in next class now.